Hi, I'm Jeff Groh, and this is Lord Kelvin and the Age of the Earth. I want you to imagine a theory created by one of the preeminent scientists of his day, Lord Kelvin. And I want you to imagine this theory is technically, mathematically complex. It contains a number of proofs, of theorems, and logical deduction. The theory is deductively sound. It's well-structured argument from beginning to end, and yet the theory is totally false, and provably so. This would be an important lesson for scientists today. I'd like to go through Lord Kelvin's derivation for the age of the Earth. This talk is based on a paper written by a student of mine named Justin McKenzie. One assumption made by Lord Kelvin in his paper is a so-called flat Earth approximation. He was able to prove that the mathematical analysis based upon assuming the Earth is flat, of an infinite depth, radiating heat vertically, would give so small an error that he could ignore that error, and it did make the analysis much simpler. My student was not satisfied with a flat Earth approximation. He wanted to assume the Earth is spherical, and that made the analysis a little more complicated. I would like to run you through that.
I suppose that we shouldn't be too critical of Lord Kelvin. There's a long history of failed attempts at measuring the age of the Earth. Sir Isaac Newton tried to experimentally, empirically determine the age of the Earth. He assumed that the Earth had been, at some point, essentially a hot molten blob of iron. What Newton did is he took iron balls, starting with 1-inch diameter, and heated them up white hot and determined how long it took for them to cool to room temperature. Using successively larger and larger balls, you could then extrapolate how old the Earth is. Sir Isaac Newton derived a value of 50,000 years, which is clearly wrong. Lord Kelvin also assumed that the Earth was essentially, at its formation, a hot blob of iron. He assumed it was about 7,000 degrees Fahrenheit, with the Earth pictured as a hot molten blob of iron radiating heat into outer space. Lord Kelvin wondered, okay, with heat radiating out, how long would it take for the surface of the Earth to appear as it does today? With the Earth radiating heat into outer space, the surface is kept at basically a constant temperature, with it really hot on the inside and cool at the boundary. Lord Kelvin assumed that the temperature, as a function of the radius of the Earth being right here, was essentially constant initially. The surface would cool down to some boundary surface temperature, and over time the cool layer would get deeper and deeper into the Earth. Initially, the rate at which temperature increases near the surface of the Earth would be quite sharp, and over time that rate of increase would get slower and slower. At the time that Lord Kelvin published his paper in 1864, having submitted it in 1862, the measured rate at which temperatures increase as you drill into the Earth was about 1 degree every 50 feet, 1 degree Fahrenheit every 50 feet. We're using the units that were in Lord Kelvin's paper. Lord Kelvin reasoned that if the Earth were really, really old, that slope would be fairly shallow, and if it were quite young, the slope would be quite steep. So he could determine the age of the Earth by the steepness of that surface temperature gradient. What age would match the currently known surface gradient? Lord Kelvin reasoned that he could apply the heat equation to the entire Earth. Heat would diffuse from the hot inner core out to the surface, from which it would be radiated out into space. The surface would remain at a cool temperature, but the heat would slowly radiate outward, and the cool layers would get deeper and deeper into the Earth. So let's derive the heat equation. We're going to begin with the continuity equation. The continuity equation says that the partial derivative of a density, this density could be a mass density or a heat density or whatever, some kind of density, plus the divergence of the momentum density is equal to 0. This equation can be derived from the divergence theorem, assuming that the only way either mass or heat can enter or leave a region is by flux across the boundary. It has to move across the boundary in order to change the total amount of that quantity, whether it's mass or heat, whatever it is inside of some closed region. To this, we're going to assume a certain way that heat flows. Heat flows so that the heat momentum goes in the direction of the negative of the gradient of the density. I'm putting a square on this to emphasize that this is definitely going to be negative. Gradients normally point in the direction of maximum increase of some density. The negative of the gradient will point in the direction of maximal decrease, and that's how heat flows. Heat goes from regions of high heat out to regions of lower heat. What direction does heat flow exactly? In the direction of the negative of the gradient. If we make this assumption, then the continuity equation becomes the rate of change of density minus k squared times the divergence of the gradient of rho equals 0. Let's move this around a little bit. First, some notation. The Laplacian is denoted by a capital delta, and it is defined by the divergence of the gradient. So the Laplacian of phi is the divergence of the gradient of phi. And in rectangular coordinates, this would be the second order partial derivative of phi with respect to x, plus the second order partial derivative of phi with respect to y, plus the second order partial derivative of phi with respect to z. This is the classical Laplacian. It follows then that the heat equation is given by the partial derivative of rho with respect to t is equal to positive k squared times the Laplacian of rho. We are going to use u in the future in this discussion, so u is k squared Laplacian of u. We also need to assume something about the initial temperature distribution through the planet and the boundary temperature of the Earth. There will be both an initial condition and a boundary condition that we will need to impose. The initial condition is quite simple. We're going to assume that the temperature at each radius between radius 0 and radius out to the end of the Earth, radius of the Earth, at time 0 is some constant, uniform, constant temperature. This is identically constant. When we write the triple equals, we mean for all substitutions of the variable, as though it is an identity. There is also a boundary condition. For all time, the temperature at the radius of the Earth is going to be some ambient temperature, which we'll denote by U with a subscript of lowercase a. Some ambient temperature at the boundary. That's going to be held constant. With this initial and boundary condition, we will be able to solve the heat equation. It's at this point that we'll part ways with Lord Kelvin. Lord Kelvin assumed a flat Earth approximation for the Earth. We are going to assume that the Earth is spherical. While I know the Earth is a little squished off the poles, we'll assume still that the Earth is a nice sphere. We will assume spherical symmetry. The coordinates are going to be r, a radial coordinate. We're going to have a longitudinal coordinate, which I'm going to call theta. Theta will be the longitude, and phi will be the colatitude. The colatitude is the angle off of the North Pole, not the latitude, which is the angle off of the equatorial plane. The angle off of the North Pole is the colatitude. So we're going to assume these as our coordinates. Radial coordinate, longitudinal coordinate, and colatitude. Assuming spherical symmetry, the temperature distribution through the Earth will depend upon the radius. It will be hotter in the core than it is at the surface. It will also depend upon time, but it will not depend upon either longitude or the colatitude. This will give us spherical symmetry. We need then to rewrite the Laplacian, which you'll recall in rectangular coordinates is the sum of the second order partials with respect to x, y, and z. We need to write that Laplacian in terms of these spherical coordinates, assuming again that our temperature distribution does not depend upon either longitude or colatitude, but only on r and t. I'm going to begin by looking at uxx, which is notationally the second order partial derivative of u with respect to x. This is, of course, derivative with respect to x of the derivative with respect to x of u. Using the chain rule, we can write this as dr dx ddr. Now, there should be other derivatives, d theta dx dd theta and d phi dx dd phi, but u does not depend upon theta or phi. And so we get, because of our spherical symmetry, this, using the chain rule. Now, what is dr dx? R squared is x squared plus y squared plus z squared, which means 2r times dr dx is 2x. The 2's cancel, and we get the partial derivative of r with respect to x is x divided by r. Let's substitute that into our formula. X over r, the derivative with respect to r of x over r, and I'll write the partial derivative of u with respect to r as u subscript r. Now, to complete the computation, we need to use the product rule. So we'll have x over r times dx dr times 1 over r times ur plus the derivative of 1 over r is negative 1 over r squared, and then finally x over r u r r. The derivative of u r with respect to r just adds another r as a subscript, each subscript representing a partial derivative. We have x over r, dx dr, well, that's going to be r over x, times 1 over r ur. Here we have minus x over r squared ur, and then plus x over r urr. Simplifying, distributing, we'll have ur over r minus x squared over r cubed ur plus x squared over r squared urr. Using symmetry, the Laplacian of u, which is uxx plus uyy plus uzz, will have three terms like ur divided by r. But we will have x squared plus y squared plus z squared, which, by the way, is r squared, divided by r cubed. That's minus 1 over r ur when we add the terms due to symmetry. And on the last term, we'll have x squared plus y squared plus z squared all over r squared. That's r squared over r squared, or just plus urr. This simplifies as the second order partial derivative of u with respect to r plus 2 over r times the partial derivative of u with respect to r. We now have a spherically symmetric Laplacian that we can apply to the solving of this problem. The spherically symmetric heat equation describing heat radiating out from a ball is going to be ut equals k squared times urr plus 2 over r ur. It is at this point that we need to make a separability assumption. In this case, the separability assumption is U, the temperature in the sphere, is going to be the ambient temperature plus a function that depends on time alone times a function that depends upon the radius alone. As time goes to infinity, the temperature should tend towards the ambient temperature. That means this term, the second term, should be transient. It should go to 0 as t goes to infinity. So in particular, this first factor should go to 0 as t goes to infinity in the second term. It may seem implausible that such a solution should exist, but by the existence uniqueness theory, if we can construct a solution that satisfies this hypothesis, it must be the solution. And that's where we're going with this. In addition, we're going to adopt a notation. When we take an ordinary derivative of some function with respect to time, we're going to denote that by a dot. If we take the derivative of some function with respect to r, ordinary derivative with respect to r, that's going to be denoted by a prime. This notation is due to Sir Isaac Newton. Newton used dots when denoting derivatives with respect to time and primes when denoting derivatives with respect to a spatial variable. So again, assuming the separability condition, u is going to be some constant plus a function of time alone times a function of radius alone. On the left-hand side, you'll get t dot times r. On the right-hand side, you'll get t times r prime prime plus 2 over rt times r prime. The derivative with respect to r applying only to r, the factor t coming along as though it were a constant on the right-hand side, r coming along as though it were a constant on the left. From here, we divide both sides by tr. Divide every term in sight by tr. We end up with t dot divided by t is k squared over r times r prime prime plus 2 over r prime. This is a function of t only on the left and a function of radius r only on the right. Anytime you have an equation with one variable only on the left and a different variable only on the right, if those two variables can be chosen independently, that shows that each side must in fact have a value independent of the other side. That means each side is constant. Just for sake of argument right now, suppose that t dot over t is some constant alpha. That means the rate of change of this function with respect to time is the constant times the size of that function. Well, that's just the natural growth law. That clearly implies that t is some constant times e to the alpha times time. Is alpha, the constant, positive or negative? Remember, in our separability assumption, we saw the function t must in fact be transient, which means it has to decay to 0 as time goes to infinity. We see that we must have alpha less than 0. We're going to set alpha to be minus lambda squared. Squared to emphasize, it's definitely negative. In which case t is going to be some constant times e to the minus lambda squared times time. Notice that I have ignored this constant. That's because the constant can be worked into r. We don't need to worry about it here. The function t exponentially decays to 0 in this fashion. So t is e to the minus lambda squared times time. The right-hand side has to equal the exact same constant, minus lambda squared. So if we rearrange this, dividing the k squared off and multiplying by r, we get 0 equals r prime prime plus 2 over r prime, and when we move this back across, it's going to be plus lambda squared over k squared r. This is a second-order linear ordinary differential equation. I'll tell you what the solution is. The solution is a constant times the cosine of lambda over k times r divided by r, plus another constant times the sine of lambda over k times r divided by r. I'll let you check this by substitution. Keep in mind that the solution is of the form some ambient temperature UA plus T times R. And what is more, if we evaluate U at the boundary at any time, we have to get that ambient temperature, which implies that R, evaluated at the radius of the Earth, must be 0. But before we apply this condition, there is another crucial observation that must be made. As you know, in the limit, as x goes to 0, sine x over x is 1. R over r. We have no trouble with this particular term, the second term. What is a problem is that first term, in the limit as x goes to 0 from the right. Cosine over x is plus infinity. This first term is undefined. It has a singularity as you tend towards the origin. That first term blows up. Nature abhors singularities, which means this term, though it is an analytical solution to the differential equation, cannot possibly be physically relevant. We ignore it on physical grounds. We have then that 0 is r evaluated at the radius of the Earth is going to be c2 times the sine of lambda over k times the radius of the Earth divided by the radius of the Earth. Well, assuming that c2 is not 0 and that the radius of the Earth is not infinite, we deduce that lambda over k times the radius of the Earth must in fact be an integer multiple of pi. In fact, a natural number multiple of pi. We see then that lambda over k is n pi divided by the radius of the Earth, where n is an element of the set of natural numbers. It's possible that we get different constants C2 for different values of n. It follows then that U is the ambient temperature plus the sum, as n goes from 1 to infinity, of Cn E to the minus lambda squared t. Lambda was k n pi over the radius of the Earth squared t, and then the sine of n pi over the radius of the Earth r over r. From here, we need to account for the initial condition. The initial condition said that at time t equals 0, u takes on the value u0. But when t is equal to 0, this factor involving t becomes 1. So we have the sum, as n goes from 1 to infinity, of Cn times the sine of n pi over the radius of the Earth r divided by r. It's at this point that we need to apply a little Fourier analysis, or Fourier analysis. This is where it gets a little interesting, because this is where the usual Fourier basis doesn't cut it. A Hamel basis is a linearly independent spanning set. The problem with a Hamel basis is that linear combinations are always finite sums. The dimension of a vector space is equal to the cardinality of a Hamel basis. One of the problems that we have here is that the cardinality of these function spaces are often uncountably infinite dimensional. No, what we need is something called a Schauder basis. A Schauder basis would have a countable list of independent vectors, and if you have some vector v, then the limit as n goes to infinity of the norm of v minus the sum as k goes from 1 to n of some ck ek. If this goes to 0, then your vector will be different from a series on no more than some set which can be ignored by the norm. These norms often involve integrals, which means that often these two vectors might differ, but on no more than a set of measure 0, say. What is more, if these vectors are pairwise orthogonal, then the Fourier series representing the vector v will be the sum, as k goes from 1 to infinity, of the projections ek, ek, ek. This is a projection onto ek. This may or may not be equal to the original vector. So, often enough, if they equal on everywhere except on a set of measure 0, that's good enough. Notice having an infinite list of linearly independent vectors implies that we are working in an infinite dimensional vector space. Whether or not vectors are orthogonal depends upon the inner product that you impose. In this case, we need to impose the following inner product. The salient point being we have a weight on this inner product. This is called a weighted inner product. And we're not going to use the usual Fourier basis. Our basis, instead of using 1, we'll use 1 over r. Instead of using the cosine of n pi over r e r, we'll use that divided by r. And also the sine of n pi over the radius of the Earth r divided by r, where n goes from 1 to infinity. If we had used an inner product without the r squared and a basis without the division by r in each case, we would have the usual Fourier basis and Fourier inner product, in which case they would be pairwise orthogonal. Note that each of these basis elements is divided by r, and we're multiplying by r squared, so these two will be orthogonal under this weighted inner product. The question is, if we have u naught minus ua, we're supposed to get the sum as n goes from 1 to infinity of Cn times sine of n pi over re r over r. This constant should be expressible in terms of these last basis elements only. Does it have any part that projects into these other directions? We can check by calculating the inner products. Calculating the product of the constant u naught minus ua in the direction of 1 over r, we'll get minus the radius of the Earth to the radius of the Earth, u naught minus ua, 1 over r, times r squared dr. We're integrating an odd function of r from negative a to a. You have to get 0. The same thing is going to happen with cosine. If I have cosine over r, 1r will cancel. I'll end up with a cosine here, which is an even function of r, times an odd function of r. That has to give you 0 as well. So we don't need either of these basis elements in constructing this constant. It will all come from these kinds of basis elements, of course, as n goes from 1 to infinity. Taking the inner product of u naught minus ua with the sine of n pi over the radius of the Earth times r over r, we get the integral from minus the radius of the Earth to radius of the Earth, the constant u naught minus ua, times the sine n pi over the radius of the Earth times r over r times the weight r squared dr. 1r will cancel, and what's left must be integrated using parts. Integrating by parts, if we set u equal to r and dv equal to the sine of n pi over the radius of the Earth r dr, then du is dr and v is minus radius of the Earth over n pi cosine n pi over the radius of the Earth r, where we have factored u naught minus ua out, ua, we get uv evaluated from minus the radius of the Earth to the radius of the Earth, minus integral v du. This minus radius of the Earth over n pi comes out, and we just have cosine n pi over the radius of the Earth r dr. This last term is a cosine function with a period of 2 pi divided by n pi r. That simplifies to twice the radius of the Earth divided by n. The length of the interval is twice the radius of the Earth. That means we're integrating this cosine function over n periods. If you integrate cosine over 1 period, you get nothing. If you integrate over n periods, you get n times nothing. So this last integral is 0. We get u naught minus ua.
Plugging in the radius of the Earth, we get a cosine of n pi. That's negative 1 to the power of n, but with one more negative. When we plug in the radius of the Earth, we'll have a radius of the Earth squared. But what happens when we plug in minus the radius of the Earth? We'll be subtracting a negative and yet one more negative. That's 3 negatives. So that negative radius of the Earth plugged in here, the negative can be ignored inside of the cosine. The radius of the Earth cancels, and you end up with the cosine of n pi again. That's negative 1 to the n with one more negative, negative 1 to the n plus 1. You end up with twice this expression. To calculate the Fourier coefficients, we have to continue the computation for the projection by taking the inner product of the sine over r basis elements. That's the integral from minus radius of the Earth to radius of the Earth of sine squared over r squared times the weight r squared dr. This requires a half angle identity. 1/2 the integral from minus radius of the Earth to radius of the Earth. Sine squared is going to be 1/2 1 minus cosine of the double angle. This last term integrates to 0 because we're integrating over full periods. The answer then is going to be 1/2 of the length of the interval. The length of the interval is 2 times the radius of the Earth. So these are the radius of the Earth. That gives us the Fourier coefficients, taking these constants divided by those. It follows then that U is equal to the ambient temperature UA plus the sum as n goes from 1 to infinity, e to the minus lambda squared, that was kn pi, divided by the radius of the Earth squared times time, times the coefficients Cn, which are these, divided by that. U0 minus UA twice. We'll have one radius of the Earth less after we cancel. Negative 1 to the n plus 1 over n pi times the sine of n pi over the radius of the Earth r divided by r. Simplifying this just a little bit, U is the ambient U plus 2 times the radius of the Earth times U0 minus UA divided by pi times the sum as n goes from 1 to infinity of e to the minus kn pi over the radius of the Earth squared t times negative 1 to the n plus 1 times the sine of n pi over the radius of the Earth r divided by r. These functions will give you the temperature on the interior of the Earth for all time. Now that we have this function, what do we do with it? Remember, Lord Kelvin's strategy was that we have some boundary temperature, and at the age of the Earth that exists at the present time, there should be at the surface a certain temperature gradient that matches the temperature gradient of this function only for one particular time. So in other words, we have to calculate the derivative of u with respect to r at r equals the radius of the Earth and set that equal to the observed surface gradient, which was 1 degree every 50 feet, 1 degree Fahrenheit every 50 feet. Once you do that, r will be evaluated at the radius of the Earth. The only unknown will be the age of the Earth, t. We can solve the equation for the age of the Earth. We're going to do the rest of our analysis numerically on Maple. I'm going to tell it to restart. The initial temperature, according to Lord Kelvin, was about 7,000 degrees, but he used Fahrenheit. So I'm going to multiply by 5 and divide by 9 to convert that to Celsius. Also, the boundary value, the rate at which U increases as you go in, I'm going to call that U rate. That was 1 degree every 50 feet, and I guess we better convert that. So first inches, 2.54 centimeters times 100 times 5 divided by 9. So that will convert to degrees Celsius or degrees Kelvin, whichever you prefer, for every meter. The ambient temperature we'll define to be 0 degrees Celsius. And the radius of the Earth, RE, is a protected value in Maple. So this is going to be 6,371,000 meters. K minus square root of 1.2 times 10 to the power of -6. I'll convert Kelvin's units. 365.24 and times 24 times 3600 there. And then what about U? That depends upon R and T. It's a function, and it's going to be equal to U ambient plus 2 times U naught minus U ambient divided by pi, we'll factor the pi out, times the radius of the Earth times the sum. And I'm going to evaluate as a floating point number the following: 1 divided by n times -1 to the power of n plus 1 times exponential function needs to be written as exp minus parentheses n times pi times k divided by the radius of the Earth squared times t. N's the exponential part, and then we're going to multiply by the sine of n times pi divided by the radius of the Earth times r divided by r. Comma n equals 1. I'm going to go up to 164. I'm going to truncate the series at that point. And that gives us the temperature distribution through the planet. And we can see how that looks. I'm going to animate U of x comma a. I'm going to not start at 0, but something close to 0. That way we avoid the division by 0 with that r equals 0 part. To REE, A equals 0 I'm going to do a whole big number here, 925377774.08. Our view is going to go from 0, REE, 0 to U naught plus 100. We're going to look at 50 frames, black color, and we'll use 200 points. Well, here's our animation. Let's see how this works. You can see how here we have r equals 0 on the left, and on the right it's the radius of the Earth. You can see how as time goes by, we slowly have a changing temperature profile near the surface, and it looks like that. Let's play this in a continuous loop. We start off with basically a flat temperature profile. The Gibbs phenomenon is quickly damped away because of this is being a parabolic PDE. Here's the surface of the Earth out here. As time goes by, this gets a little bit cooler towards the surface. The surface gets cooler and cooler, and you can see that cooling on the surface here. The deep core is still hot as the day it was formed, but on the surface, not so much. Here we're going to about 92.5 million years. Instead of animating, if we instead plot kind of a tangent line here, representing how quickly the temperature increases as you go in, you can see that we get a pretty good match here at this 92.5 million years using Lord Kelvin's model. Using this particular model, Lord Kelvin would have declared the Earth is 92.5 million years old, except it's not. And people, even at the time of Lord Kelvin, knew there's no way the Earth was only 92.5 million years old, based upon the rock strata and the fossils available in the rocks. There's no way the Earth could only be that. In fact, in Lord Kelvin's original paper, he predicted the age of the Earth was somewhere between 10 million years. And as time went on, he allowed that to vary between 10 million and 400 million years. If you run this simulation to 4.5 billion years, which is our current estimate for the age of the Earth, the temperature profile is going to be like this, which means, and here's that little line giving you the gradient at the surface for the temperatures near the surface as measured and used by Lord Kelvin in his model. You can see that Lord Kelvin's model does not match what happens for a 4.5 billion year old Earth. So the question is, where does Lord Kelvin's model go wrong? His model predicts a young Earth than it is observed to be. So what is keeping the surface of the Earth warmer than Lord Kelvin's conduction model would allow? And the answer is a couple different things. One is convection. Most of the error in Lord Kelvin's model comes from convection. Hot magma from the center, from deep within the Earth, wells up to the surface, warming that surface in ways that Lord Kelvin's model does not allow. Lava flowing from the center up to the surface, warming the surface. If you allow for that convection as well, you get at least 80% of the error in Lord Kelvin's model. And if you allow for the radioactive decay of radioactive elements through the Earth, you can get up most of the rest of that error as well. Of course, in Lord Kelvin's day, they didn't know about radioactivity, so there's no way they could have accounted for the extra heat source from within the Earth. Lord Kelvin was also the victim of confirmation bias. He did not know about nuclear fusion either, hadn't been discovered in his day. So he thought all of the heat radiated from the sun comes from gravitational contraction of the sun itself. The sun is getting smaller, it's more compressed because of gravity. And when you compress a gas, it gets hot. Gravitational contraction and compression of the sun would produce heat. In fact, most stars start their nuclear fusion engines with gravitational contraction, heating the gases to the point where fusion reactions can begin. Once the fusion reactions begin, so much energy is created, it holds the star up and out and doesn't allow for that gravitational contraction to contribute a whole lot to the brightness of those stars. Lord Kelvin didn't know about nuclear fusion. He thought all of the energy coming from the sun came from gravitational contraction, and he predicted as a consequence that the sun couldn't be older than 10 million years. So he was confirmed in his view of a young Earth based upon his theories about how the sun produces light and couldn't be more than 10 million years. He never gave up on his model. To his dying day, he believed that he had gotten it right. And this is an important lesson for us today. How did Lord Kelvin get it so totally wrong? Well, he failed to take into account convection of heat from the interior of the Earth. One of his students pointed this out to him, but he refused to believe that that could be a meaningful error till the day he died. It's important to understand this example because this example shows how a preeminent scientist, one of the cream of the crop, tip of the top, could get something so totally wrong. Truth is not determined by the eminence of the scientist or by the elegance of the mathematical analysis, or even the difficulty of the mathematical analysis. Sometimes that difficulty is just diversion from the fact that the theory is just untrue. So keep this in mind when you study scientific theories. Don't base your confidence in the theory on the eminence of the scientist involved or the elegance or complexity of the analysis. It comes down to observable evidence. In this case, the observable evidence contradicts Lord Kelvin's theory, and so he was wrong.